Have you ever wondered how we can identify patterns in the wild and really find them fast? Like, for example, if you're looking for your friend in a fair, you can spot them fairly quickly in a very, really crowded scenario, right? If we want to enable robots to do the same, to find and rescue survivors in the wild, the question is how would we enable these robots with these superpowers, right? We are going to look at one of the simplest and the most pivotal methods to do this today called convolutions. So let's dive right in. So let's take a simplified example on an image processing problem. You might have played this game as a child wherein the goal is to find this character called Waldo. You're given this massive image with a lot of people in it and you want to find Waldo, right? And this is what Waldo looks like. And the goal is to find Waldo in this image, right? I want you to pause the video and spend a few seconds like trying to find Waldo in this image. And if you found Waldo, this is where Waldo was. He was on the top right there, right? Awesome. The question is, how can we make a computer do this, right? Let's take a very simplified example of finding Waldo and then do the same procedure there. And then we can go on to build methods which we can actually use to determine how Waldo looks like. Let's take a simple image. In this case, it has like three simple shapes: the circle, the square, and the triangle. Let's say we have an image of what we are trying to find. In this particular case, the triangle. To make life easy, I'm going to say that I know the exact orientation and the size of the triangle I'm looking for, not to make it too complicated, right? To make it even more simpler, I am going to throw away the colors. I'm going to say this is just a grayscale example. Life is simpler with this example to explain, but remember that we can do the same exact math for color images. Everything is going to be done 3 times for R, G, and B, right? I'm going to call the full image where I'm trying to look for this stuff called the image I, and I'm going to call whatever I'm looking for the template T. Remember that template is the thing I'm looking for, and image is the entire search space where I'm looking for this template. What I'm going to do is I'm going to take the template T and place it on the left top corner of the image I, and I am going to basically look at the crop or the patch which the template T overlaps the image I. Once we put the template on the image, we are going to take this template and move it all around. And this is in a method called sliding windows. So we are essentially sliding the magnifying glass all over the image, or we are essentially sliding how we would clean a window, which is basically have a small piece of cloth and we would slide it all over to clean the windows. This is exactly the same concept. This is going to be called the patch P. So this is what it looks like. In this case, it's the off-centered circle, and I'm going to call this the patch P. I want to essentially come up with a function which gives me the similarity between the template T and the patch P. If you're wondering why do I need that? Because remember that it's almost like you going through a magnifying lens and looking for the Waldo like before, or in this particular case, the triangle, and you're zooming into that with your magnifying glass and saying, hey, is there a triangle here or not? We need a mathematical toolkit to say if there is a triangle here or not. And that's going to be through this function f, which we are going to call is the similarity between patch P and template T, right? Patch again is the crop of the image I below the template T, as we are seeing here. And we want this function f between the T and P, and as we were discussing before. Great. So the idea is that as we slide this like zoom lens or basically the patch or the template around, different patches will give you different scores. And when you land it on exactly the triangle, you're going to basically get the function between the template and the patch, right? And again, just this is the similarity. We want the similarity to be high when it lands on the triangle. We want the similarity to be lower when it lands on the circle or the square, right? And depending on what this number of similarity is, we can pick and say that, hey, this is the triangle, right? Great. So how do we measure similarity? In other words, what is F? One of the simplest methods to do this is called correlation or cross correlation. In this case, you're just literally multiplying the pixel values between the template and the patch, right? And this is what it looks like. And if the shapes align, you're going to get a maximum value. And if the shapes do not align, you're going to get a smaller value overall when you sum them all up or take an average or a mean, right? Great. This is what it looks like. In this particular case, the triangle and the circle is going to be a small value, so that's a bad match. But the triangle and the triangle is going to be a large value, which is an amazing match. That's the idea here. Great. Just to quickly recap, correlation or cross correlation is the measurement of similarity between two signals or sequences. In our particular case, the signal or the sequence are basically the template and the crop patch of the image which is behind the template. And we are going to slide this template around like a magnifying lens going through the entire image through and through. And we are basically cropping the part and we are trying to measure the similarity through just multiplication of element-wise multiplication and summing them up, right? So if you were to do like correlation of the same image with the same image or the same signal, what does that give us, right? I want you to take a second and think about it because this is super important. This is called autocorrelation. And the question is, why do we need this? This helps you understand the momentum of the signal or how the signal is changing. And this is used a lot in the stock market to understand where the trend is going, right? And it's a super useful thing. And this is also somewhere useful in computer vision certain times to see how smooth a signal is and so on and so forth. The question is, we have correlation. If we have three elements, A, B, and C, we correlate A and B, and then we correlate the sum with C. Can we correlate A and B together and then use the result with C? Can we stack it? The question is that. The answer is no. Correlation is not associative, so we cannot stack it, right? Remember in the Fielding Waldo example, this is what correlation looks like. You have the picture of Waldo. Again, remember that this is an enlarged image of Waldo, but we have it for the perfect size just to make life easy. And then we basically go element wise and then we do multiplication. Remember in the previous example, we had a grayscale image where it was very easy. In the RGB image, you're going to do this for every channel, red, green, and blue, and then sum them all up together, right? The same idea. But we have an amazing toolkit called convolution in mathematics, which is in contrast to correlation. I'm going to just play the slide one more time. I just want you to observe there is one difference in the equation, but the equation looks the same, right? If you were very observant, you would see that the sign basically instead of being plus, it actually flipped to the negative sign. Essentially what we are saying is take the template image and then flip the template image around, right? And this is what it looks like. We flip Waldo image upside down and left to right. So flipping this image in a way makes it so that the convolution has some amazing mathematical properties, as we will see later. And it essentially gives you the area under the curve where we are matching the template to the image. And that has beautiful properties as well. And this has nice, beautiful properties in mathematics where it goes very well with the Bayesian distributions and so on, which I'm just giving you a hint on. Great. Just to see what convolution looks like, the image on the back is called the source image. The thing in the middle is our template called the convolution filter. And the thing on the bottom right here is essentially what we are getting as the value. Remember that the higher this value, the more this convolution value is. Again, the more here could be in either negative or positive direction. So we will essentially take the absolute value here because that's all we care about, right? Because we don't really care about if it's being positive or negative, right? And the way you would do convolution is you would do, you would take the kernel, you would flip it left side down, left to right and up to down. And you would basically multiply it element wise and add them or add the all values up. In this particular example, the convolution filter is already pre-flipped, so you don't have to flip it all over again. This convolution filter in the lingo of mathematics or machine learning or deep learning is called a kernel H, or can be represented by H or K, depending on which community you're talking to. This is generally denoted by this cross with an O or a star. And convolution, you can flip the order of the elements and the convolution will still be valid. It will give you the exact same result. Just to quickly recap, the convolution filter is in yellow and it's sliding over, and the final answer is shown on the pink on the right side here. If this was unclear, I would say go back and refer to the video one more time, because this is super important and we are going to build upon this concept in the next few slides. Great. Let's play a small game. Let's try to guess what can happen if we take the image on the left, we take the kernel on the right, and then we convolve, right? Remember that it's a color image here. And when I say I'm convolving it with this kernel on the right, which is just a 2D thing, it means that I'm replicating this in red, green, and blue channels. And I'm going to do this for red, green, and blue channels again. And I'm going to combine that image and stack it and make a color image. In this particular case, I'm saying it's a 3x3 grid, and I take the center value and I basically multiply it by 1, and I take like the 3x3 neighbors around it, I multiply them all with 0, I add them all up, and that becomes my final image. Obviously, multiplying with a 0 means that you're not using that value, you're only using the center value. Essentially, wherever this kernel goes, I only take the pixel which it's landing on, and I take that value and I copy it back to the destination image. As you would have guessed, this returns the original image. This is called the Dirac delta function, or the identity convolution matrix, right? Which means that it didn't change anything. Now let's look at a different kernel. Here in this case, that 1/16 is just there to normalize so that we don't increase the average brightness of the image. We are essentially taking the weight of the center pixel where it's lying on more, and we are taking lesser and lesser values as we go farther away from the pixel, right? You're adding essentially the current pixel plus a little bit of the component from the neighbors. You can sort of think of this as like if you live around like 10 neighbors, you basically are sharing the culture with them, right? What will essentially happen is you average out the culture, right? And it's the same thing that's going to happen here. You're going to average out the pixel value. And as you might have guessed, this will lead to a blurrier image, right? The bigger this kernel, the more blurry it will get. And in this particular case, the blur happens to be in the form of a Gaussian distribution, right? And this is called the Gaussian blur kernel, and it Gaussian blurs the original image. In the next example, we have a few negative values, and we are bumping up the value in the center. So you can think of it as you take the pixel behind you, you bump up the value, and you take your neighbors and you basically say, hey, I don't really like my neighbors, so I'm going to subtract the value there. So essentially what this helps you do is it helps you distance yourself more from the neighbors. In other words, it increases the local contrast of the neighbors, right? And this essentially gives you more sharpness, and this is called the unsharp mask filter in Photoshop. So let's look at one of the best thing about convolution, because we said like it has beautiful mathematical properties. Let's take this image of a Yamaha R6 motorcycle, and we have a horizontal Sobel kernel, as it's called. Essentially, if we run this kernel through, we will see all the horizontal edges here, right? So that's the idea. And if we do the same thing with a vertical Sobel kernel, we will see all the vertical edges, right? What if we want to basically come up with a filter which gives us both horizontal and vertical Sobel filters? The question is, can I just pre-combine the filters SX and SY I saw before and just run it on the motorcycle image? Does it give me both? The answer is an absolute yes. And that's one of the best thing about convolution, that it's associative in nature. So what I can do is I can have a really complicated kernel, set of kernels, and I can pre-combine all of them into one simple matrix and basically just convolve that with the image to find that pattern. Remember our Waldo example? We can say like, I want to have the Waldo's hat, I want to have the Waldo's hairstyle, I want to have a kernel for Waldo's eyes, I want to have a filter for Waldo's nose, I want to have a different filter for Waldo's mouth, and I can easily construct filters for each of these features of Waldo and pre-combine them, and that becomes my feature of Waldo. And that's the best thing about convolution, that it's associative. So you can pre-combine and pre-compute filters. This saves you a lot of computation because you don't have to do this over and over again. So this is what we were talking about, right? And just to give a quick primer, so like when neural networks were initially implemented, mathematically they all used convolutions, but because these filters were learned, as we will see in the later videos, they were replaced with correlation, because then the filters were learned in that way that like associativity did not matter much. But most of the classical algorithms and even neural network compression algorithms still use convolution extensively, and it still remains to be one of the most amazing concepts in computer vision and image processing. Just to quickly recap, convolution is the calculation of area under the product of two signals, and it works as a filtering operation. So you can pre-combine multiple filters together, and you can utilize them to filter and look for something like Waldo or the traffic cylinder we talked about before. So like thing we were talking about in the template matching is called sliding windows. The question is, why do we need to have sliding windows? Why can't we just do it in single go? What is the difference between correlation and convolution? And what is the coolest thing about convolution? See you next time. Take care. Bye.